Up till now, we have talked about subnetting based on the number of networks you need, the number of hosts per network that you need, and now we've fallen into what I call reverse engineering a subnet problem, which is actually probably the most common thing that you will do. It is extremely common to walk into an environment where you see an IP address and a subnet mask, and you need to find an answer to the question of what network is that IP address on? Or what would be another host on the same network as that IP address? It's best explained with an example. So let's jump back in the pool again, right? So we've got a computer here, we'll say a happy computer, has the IP address 192.168.1.127. Now, in the real world, you may be saying, okay, well, this guy maybe can't connect to the internet, or can't ping some other device. What's wrong? And so you want to find out what other devices are on the same network as this one. Or on a certification exam, you might be asked the question, you've got happy computer here. What would be the broadcast for his network, or what would be his network ID, or what computer would be on the same host, A, B, or on the same network, A, B, C, D, and you got to pick it from a lineup. So regardless of what situation you're in, you have to work backwards. In my opinion, you can do these much faster than the previous examples that we've seen in the last nuggets, finding the number of networks and finding the number of hosts, because they've actually given you the answer. Well, at least from the perspective of what we were trying to find previously. Remember, previously, we were like, okay, we've got this network and we need 30 hosts per network. So what subnet mask will do this? And what are those ranges? Well, in this kind of thing, they're kind of like, well, we aren't really giving you any of that. We just say, somebody figured out that they wanted to use this subnet mask. So now they're asking you to work backwards, or essentially maybe work forward one step, because remember, step one was convert it to binary. So if you had 30 hosts, you would convert that number to binary. Step two would be to reserve the bits in the mask and find your increment, and then step three would be to find your network ranges. So essentially, with this problem, you're starting right here. You've found the subnet mask, if you will, and now you just have to find the increment and then find your network ranges. So let me ask you this. If somebody threw a subnet mask at you and said, hey, here's a subnet mask, what increment does it have? What increment would I use for my step 3? How would you approach it? Well, you would say, okay, well, what is the increment? The increment is the lowest network bit converted back to a decimal number. So looking at this, I need to find out what the lowest network bit is. Now, if I take this, it'd be a whole bunch of ones. Well, I'm not really concerned about all of these ones right here, because they're not going to give me anything. I'm really concerned at where the lowest network bit is, that 224. So if I convert that to a decimal number, it would be 1, 2, 3, 0, 0, 0, 0, 0. That's the binary version. Did I say the decimal number? If I convert that decimal number to a binary version, it would end up being this. So then I would look and say, okay, well, lowest network bit as a decimal number, that would be what? 32, right? Okay, so I've now got this magic number, if you will. Let's jump back to the original. I would look at that and say, well, at some point they had to start from 192.168.1.0. I mean, they have to start from 0 at some point. So I would then say, okay, well, let's do 32, 64, 96. I'm just adding my increment right here. 128, well, actually, stop right there, because I passed 127. That's my IP address. So I would then, again, if you want to, you can fill in all the ranges, but really the only one I'm concerned with is this one. So this happy computer comes from the network 192.168.1.96 through 127. That's his network. And whoa, hello, major problem. What's wrong with this picture? 127 is what? The broadcast address of that happy computer. He's not happy at all. He's not working because we assigned him the broadcast IP address for the network. He's not going to function. Now, matter of fact, if you try to assign that IP address in Windows or OS X or whatever operating system, it will give you an error because Windows is smart enough to say, "Whoa, that's not a valid IP address. Try that again." But that would be a great test question where they're like, what's wrong with that guy? And do you see? You wouldn't be able to tell what's wrong with that guy without really figuring out the network ranges. I mean, if you didn't see this, if that was hidden from you, they're like, well, what's wrong with that? You're like, I don't know. What's wrong with that? You tell me. Because from my perspective, it's just an IP address, but the subnet mask puts it in such context. Okay, let's do another example of this so you can see just how key this skill is and how tricky the questions can be. Let's just say this is an exam situation or maybe even a real world situation where they're saying, hey, this host cannot surf the internet. They're not able to get out and do their day-to-day functions. Please identify what's wrong with this picture. Now, of course, in the real world and on the exam, of course, it wouldn't be just left to this. There would be a lot more distractors in there. There would be, well, is the internet up? Is that, how many other routers, how many other hosts are having this issue? I mean, there's be a lot of other distracting things, but let's just focus on the core. We've got this host who has this IP address, 172.16.68.65. His default gateway, and they line up, is 172.16.68.62, which looks good, because that's the IP address assigned to the router that, and down here is the internet or whatever network we're connecting to. Okay, well, it seems okay. Well, let's reverse engineer it and see if we can figure out. We look at that subnet mask. We've got 3 octets of 1s. That's the class C. And then let's see, this last octet would be 1, 2, 3, 4, 0, 0, 0, 0. That'd be it if we're converting 240 to binary. And you will get used to a lot of like what? Well, 240 is 4 bits. 224, 3 bits. Those kind of things. So we look and we go, okay, well the increment. That means the increment is 16. Okay, well let's do this. So we go 172.16.68. Well, they would have had to have started at 0 at some point, so I can go, okay, 16, 32. I'm just counting up until I can pass those networks. It would be 48 plus 16. That's where my muscle memory wears out. So it'd be 64 plus 16, that'd be 80. And okay, I've stopped. I've passed those, so I can start filling in the end range. This goes through 47. This goes through 63. This goes through 79. Whoa, wait a sec. Oh, wait a second. Okay, stop the train. First off, are either of these IP addresses invalid? No, they're not. The router happens to have the last valid IP address from this range. The router is in 172.16.68.48 through 68. He's got a valid IP address. It's not a broadcast. It's not a network, but it's the last one from that range. And this computer happens to have the first valid IP address from this range. What's the problem? 65 is not the network. It's the first real IP address. The problem is they're in different networks. Even though they're plugged into the same network, they're in different networks. Now, that doesn't work. That's what a router is supposed to. A router is supposed to be the one that moves you between networks. As in, the router should be in your network. Like this host should be in the same network as the router, and then the router would move you to, say, that network or some other network that you're trying to reach. You can't have the computer be on a different network than the router that's supposed to get him off his network. Does that make sense? So therein lies the problem. Now, do you see how tricky that could be? Because you're looking, you're like, first off, if we hadn't broken that out, this totally looks okay. We would look at this and go, well, 65, 62, they seem close together. They're only 3 IP addresses apart, right? It seems like that should work okay. So you wouldn't even know until you reverse engineer it and find this. Now, expect, if you're planning to get certified, that this will be embedded in a much bigger, more complex situation that involves NAT and all the other technologies that are out there. And they're like, okay, well, try and figure out what's wrong. And you'll be thinking of really advanced stuff, but then you're like, oh, wait, these guys are in different networks. That's why I say this form of subnetting is probably the most common kind of subnetting that you're going to encounter. It's because it's so easy to write a question for it, but also so common of a situation where you want to figure out what network a device comes from. Okay, at this point you have seen subnetting based on the number of networks, hosts, and reverse engineering a subnet mask. If you've got all that, if you're like, okay, I got those skills, I would call you a subnetting quasi Jedi. And the only reason the quasi is in there is because you probably just need more practice to solidify those skills. There is one more method, and that's VLSM, but you'll find in the next nugget that it's nothing new. It's just doing what we've seen already again and again and again and again. So before I launch you into VLSM, I want to make you aware of a rule. And the only reason this rule exists is because we as humans don't think about zero. As in, if let's say you had a cell phone in your hand, and somebody looked at it and they're like, "Oh, well, how many of those cell phones do you have?" You would look at them, you'd say, "Oh, I just have one cell phone." Now, the person you're talking to wouldn't interpret that as two because you said one. They wouldn't say, "Oh, well, there's the zero value as well, so you must really have two cell phones." You see what I mean? But a computer does. A computer counts zero as a value, even though it's really zero value. Or for example, if there were paper clips on your desk and you said, I have 10 paper clips, the person wouldn't think, well, you must really mean 11 because 0 through 10 gives you 11 values. But computers do. And it's the same thing when you're working in binary. Computers count that binary zero value. So these values might throw off your calculations, but if you're aware of the rule, it really becomes a non-issue. So for example, let me give you a scenario here. If somebody said, take 192.168.1 and break that into 4 networks. You would look at it and go, okay, great. Let me lay out my binary chart, 128, 64, 32, 16, 8, 4, 2, 1. So you'd go, okay, step 1 is to say how many bits to get the number 4. And I'd look and I go, okay, well, the 4, 0, 0. Then it would be 4. And you would say, okay, well, 3 bits to get the number 4. Well, in actuality, because of the zero value, you can get the number 4 with 3 bits. I say, well, how's that possible? Well, if you look at this, you've got 2 and 1, which gives you 3. That's the biggest number you can get with 2 bits. But then we start working it down. We go, okay, well, there's 2, there's 1, and then there is 0. Or binary values would be 0, 0, 0, 0, 1, 1, 0, and 1, 1. Those are the binary values. So you can actually, the truth is, you can get 4 networks with 2 bits because of counting from 0. So essentially, if you look at the binary chart and there's any kind of question asking you to figure out how many networks and it's an exact binary number, you just have to remember, well, okay, binary always counts from 0, so we can just simply subtract 1 when we're doing that. Now it's similar on the host side, slightly different, but similar on the host side. Because of the 0, but it's somewhat offset. Let me explain. So let's say you've got the same situation, 192.168.1.0, and someone says, okay, I want you to subnet that into networks of 7 hosts per network. And I would say if they're asking that, they're probably trying to trick you or something. 7 hosts per network. And you would look at that and you would go, okay, well, step 1, let's convert 7 to binary. And I would go, okay, let's say, okay, 1, that's where my first one would go. 2, 3. So all 3 of those bits, 1, 0, 0, 0, 0, 0, 1, 1, 1 is how I get the number 7. Well, therein lies the problem that we're after the number 7. So we would say, okay, it takes 3 bits to get the number 7. So in the next one, step 2, we would save 3 bits. We would go, okay, well, we start with a /24, which is a whole bunch of 1s, and we go 0, 0, 0, 0, 0, 0, 0, 0. Is that 8? That's amazing. How did I do that? So we would save 3 bits. So I would say 1, 2, 3 are saved. So these would all flip over to the network side. So that'd be right there. So our increment would be an 8, right? Well, there's our problem, because when we start doing our increments, we have to start realizing we're going to go 192.168.1.0.1.8.1.16, down and down we would go, and we'd fill this in, and we'd go, okay, well, it looks like we've got 8 IP addresses, but therein lies the problem that we actually only have 6 valid addresses. We end up 1 short. Now, how did that happen? Well, we ended up 1 short because we always subtract 2 from that value, right? We always, whenever we're saying 7 hosts per network, we always have to think, well, but we also have to account for the network in the broadcast. But it somewhat gets accounted for because of the 0 value, because of 0. But so 0 covers one of the IP addresses that we would be short, but we are still 1 more short. Does that make sense? Because there's a network and there's a broadcast. So 0 covers 1, but we still end up 1 short. So here's the exception. To be safe, always subtract 1 when finding networks. It'll never hurt you to subtract 1 when you're finding the number of networks, or always add 1 when finding the number of hosts per network. If they ask you to calculate 7 hosts per network, calculate 8. If they ask you to calculate 101 hosts per network, calculate 102. It will never harm you to add 1 to the value, nor will it harm you to subtract 1 when finding the number of networks, and that will be the rule. When you get to the point where you just get so familiar with how binary works, you just look at it, it'll sound a red flag. When you see something that you're like, wow, they're asking for exactly the binary number. Okay, that's going to give me it'll just send that spidey sense that you get inside of yourself when evil is about to attack you. It's that same kind of thing. When you're seeing enough of these subnetting problems and you're like, ooh, they're asking me for something weird. Like, why would they ask me for 15 hosts per network? And when I figure that out, it comes out to a binary value of a solid 1 block. Okay, let me just spidey sense is going off here. Something's wrong with that situation. So you'll start to navigate and figure it out on your own. But if you want a rule to remember, that will be a solid rule that will never fail. All right, well, you are well on your way to subnetting mastery. One more topic coming up, and that is variable length subnet masking. But for now, we have seen reverse engineering, which is the third and final method of subnetting that is very unique. And then we saw, of course, the great exception. I hope this has been informative for you, and I'd like to thank you for viewing.